At this point, we've gone over a lot of parts of the engine, but we haven't yet said anything about the induction of air into the engine. Now, this is critical as that's kind of the heart of the whole cycle, is taking that air and putting fuel in it, squeezing it down, throwing a spark to it, and then boom, moving that air out in the exhaust cycle. So let's talk about just reciprocating engine induction theory. Like what is actually happening? Why does it work the way that it does? And then how do we go about using it inside of the engine itself?
Okay, so let's just kind of levelize our understanding and just review some terms. Now, the induction cycle of the engine, or the intake cycle, the suck cycle, is bringing air into the cylinder, is what we're going to be talking about. Now, that happens via the intake valve on the cylinder itself. Now, you can imagine that as that cylinder goes down, it's happening very, very fast. The valve opens, and all that air coming from the outside of the airplane is getting sucked into the cylinder in a very rapid fashion. Now, if you remember our gas laws, as speed increases, pressure decreases, and that pressure decrease then causes a temperature decrease. That's then offset by the cylinder head temperature and all that good stuff. Now, so that is when we talk about the induction cycle. We're inducting air into the cylinder. Okay, so where does the air begin its journey? It actually comes in through the cowling. Now, if you'll look just above the nose gear there, and right below the landing light, is a square hole in the cowling. That's actually the inlet air scoop. That's where the air that's going to be inducted into the engine enters the engine. Now, if you're used to working on like lawnmowers, weeders, that kind of thing, you have a downdraft carburetor that's actually sat on top of the engine, and the air is drafting down using gravity for its for its benefits. Not so much on airplanes. For a variety of reasons, the carburetor is going to be located on the bottom of the engine, and air is going to come in through that cowling right there and then go up. So more like a updraft carburetor. But we'll talk about fuel metering systems at a later class. But that is where the air is going to start its journey. Now, if you imagine that same inlet is on the left-hand side there, where it says air filter, that's where the air is going to come down into the engine. It's going to go down through a filter. We'll talk about it here in a minute. Through an air duct, and then into a plenum that goes up into the carburetor itself. Now, once the air has been combined with fuel and properly atomized, there will be further duct work to take it up into the cylinder, also known as the intake manifold, will be, and that becomes really important whenever we start talking about like superchargers and turbochargers and that kind of thing. But for right now, just understand that is the path the air is going to travel. It's going to come in through the front. Go through a filter, then come down into that plenum, and then into the carburetor, and then from carburetor goes into the engine. Now, that is, if you end up having a engine that ends up having a power generation problem, this is most likely where the problem is going to be at. It's either going to be this or fuel. And I'll tell you a story. Now, granted, this was a turbine helicopter, not a reciprocating engine, but it's the same concept, same idea. Okay, so this is a engine barrier filter system. So what you see there, those red coils, that's actually a filter. It has wire mesh on either side with this felt-like material that's sandwiched in between them. Now, it's a pretty expensive system, but it was made to stop from having to either use a particle separator, which we'll get to in turbine engines, or have replaceable filters like you would have, like say your 172 or whatever. What we would do is we would take those filters, and you would wash them all out and get all the dirt and grime off of them, and then you would let them dry, and then take this K&N air filter oil, and you'd oil the filters. Well, there was never a good standard on how much oil you should put on the filter. Some people would put it on and there wasn't enough. Some people would put it on and it's way too much. I don't think in years of working on helicopters with those particular type of filters did we ever come up with a solid standard for what EBFs should be oiled to, and some reliable way to make it work. So one day we get a call that we've got a helicopter that has that failed a power assurance check. So basically, before they took off, they pulled power and they realized there just wasn't enough power to get the helicopter to come up off the ground reliably. So it was unsafe to fly. And so since they were on the ground, they didn't actuate the bypass door, which you can kind of see in this picture. It's right there on the bottom with this big wire mesh grate on there. And what that does is if the helicopters fly along, the filters get clogged, they can flip a switch and it'll throw the bypass door, but then you have to change the engines out and it's a bunch of drama that comes afterwards. So a lot of people don't try not to do that. So since they were on the ground, they simply just shut the helicopter down and they called us. So I get out there and it's not making enough power, so it's either going to be fuel or air. Well, the first thing it is, I took the cowling off and looked at those filters, and they were absolutely muddied up with just dirt and grime and gunk. And what had happened is that there were new filters, they were over oiled, and then they landed in a really dirty environment, which then just basically clogged those filters up to where the helicopter simply just could not breathe enough air. Now, it's breathing a lot of air because it's a turbine, helicopter, so it's just drinking a lot of air on a regular basis. But it's no different than a Cessna 172 or a 737 or anything else like that. In order for an engine to make the right amount of power to get the plane off the ground and keep it off the ground, it has to be able to access the outside air with a reliable volume. If you have anything that could prevent that, something like I've seen bird nest in induction channels and engines. I've seen clogged filters, obviously, all kinds of different things. Any of those things that prevent air from flowing through there will cause the aircraft not to generate the appropriate amount of power. So that's why, understanding the way that the induction system works and understanding how to troubleshoot it and when to know or how to know, whenever you're seeing a troubleshoot or a induction fault. And knowing where to go look and try to find whatever that fault is and fix it is really, really important. So this kind of your conclusion to kind of induction theory. Let's see what we have next.
Now we know that as pressure increases, temperature decreases. Now let's kind of think through this. If the pressure is decreasing, or the temperature is decreasing, and you already have cooler temperatures, some moisture in the air, what are you going to get but ice? And so induction system icing is something that's ubiquitous across all power plants. It doesn't matter if it's turbojets or reciprocating engines. Induction system icing is something that we constantly have to war against. And so let's talk about why does it form, how does it form, and then what are we going to do about it?
Now, there's three types of induction system icing that we have to be wary of. First off is impact ice. Now, this is as the plane flies along, effectively what you're doing is just giving that air, which has a high moisture content and it's sufficiently cold, a place for ice to form up on. As the plane flies along, that cold air hits a single spot, in this case inside the induction system, and you start to cool it off to where it starts becoming very, very conducive to freezing in in this case this little elbow area inside of the induction system. Now the next one is throttle ice, and that's where the throttle plate, it's especially susceptible whenever it's not fully open or fully closed, but it has that that angle that constricts the space. The reason being is a good thing. Back to our gas laws, right? As that space constricts, pressure is going to decrease, and as well as temperature, because the velocity is going to increase. Which then means if that air is just kind of on the the cusp of starting to freeze, well, now it's you give it that little extra push for that throttle ice to start to form, and then this could be really really dangerous because it's going to cause that throttle plate to stick into place, if not just cut air off entirely to your engine. The last one is a fuel evaporation ice. Now this one's probably out of all of them the least common because as long as you have the correct gas in there and you've sumped the tanks and all that good stuff, you shouldn't have a whole lot of moisture in your gas. However, there's always going to be some, and so what's effectively happening is that there's moisture inside of that fuel, and as it gets put into the induction system, that fuel starts to separate from the water, and that water then, because it's sufficiently cold, freezes on like the sidewalls of your induction system, and then it starts to cause a ice blockage. So those are your three fundamental types of induction system icing. All right, so to kind of give you an idea of what that throttle icing could potentially look like, this is a picture of a carburetor that was pulled off that during an icing situation, and you can see how it just totally blocked the ability for the engine to take in air, as well as start to freeze those throttle plates into place. Now, the most distinguishing symptom of carb icing is that the engine will stall repeatedly during warm up. But however, if you're flying, you'll start to see a loss of RPM slowly, and then eventually it'll start to like sputter because it's just not getting enough air to keep it going. All right, here's an example of impact icing. Now this is on a wing, and you can see like there's like de-ice boots underneath there that obviously hasn't worked. But you can just imagine this is inside of the induction system. So as the plane flies along and encounters icing conditions, and then all of a sudden ice starts to accumulate on anything that it can potentially accumulate on. Now imagine this is inside of your induction system where the space is already confined, a little bit, and then all of a sudden ice starts to form, further constricting that space. Now the engineering is basically got it laid out to where it needs every bit of that space for the engine to operate appropriately, and your landing your rolls, your takeoff distances, everything, your VX, VY, all of it is all based on the engine operating at normal capacities. And all of a sudden now you've introduced ice into the situation that then starts to restrict what that engine can actually do. Okay, so lastly, this is a laboratory duplication of ice crystals clogging a fuel oil heat exchanger on a Trent 800 engine. Now, this basically goes to show you the amount of water that's actually in fuel, and if exposed to freezing condition, the fuel could potentially freeze. That's why on large turbofan engines like our JT9s, there's actually a fuel heater, and the reason being is that they want the fuel to be of sufficient temperature to make sure that this doesn't happen. Because if this starts to happen, the plane's probably going to hit the ground before the fuel actually unfreezes. Because some of these places that the fuel has to go through are very, very constricted, and so this is just another example of how your induction system could be clogged with ice.
On a reciprocating engine, the main mitigation factor for induction system icing is carb heat. Now, carb heat is interesting because it's actually degrades engine performance fairly significantly. Matter of fact, if you're going to take off in the plane behind me, whenever you're doing your run up, one of the things you're going to do is you're going to pull it to idle. You're going to pull the carb heat out, make sure the engine can still operate even if you were at idle with the carb heat pulled out, because it really puts a large tax on the engine to have that carb heat operate, to try to bleed off some of that induction system icing.
Okay, so this is the kind of overlay of how the carb heat system actually operates. Now, you got to think about how does icing form. Like, you remember your gas laws, it squeezes, the air gets squeezed down, the pressure drops, ice can then form if there's sufficient moisture in the air coming in, which a lot of times there is. So the only real answer to that is heat the air back up. Well, there's only really one good way to do that on a reciprocating engine. That's by simply taking air that is being pressurized on the top of the cowling, that's being pushed down over the heating fins of the cylinders, and that that heat is stripped away, we take some of that heat and then put it into our induction system, and that helps melt the ice, because what you've effectively done is taking air that's been super cooled and then warming it back up with hot air that's coming off of the top of the engine. Now, as you put those two together, you have other effects that you probably don't want, like degraded engine performance, because as the air heats up, the molecules push away from each other, so there's less molecules of air per given space of air coming into the engine, and so therefore there's less fuel because you have to have a 1-to-1 ratio. Now, if you do that as it comes in, the engine will produce less RPMs. It may start running rough and all the good stuff. That's why on your run up, you're always going to check and make sure that the engine can run even with the carb heat open, because it doesn't do a whole lot of good to turn the carb heat on just to find out that the carb heat kills the engine because the idle is not set right, or whatever issue you may be experiencing. All right, and this is what that actually ends up looking like. You can see the carb heat is being pulled off of the shroud around the muffler there and being piped directly into the carburetor. Now, there's a door that basically leaves that sealed off under normal operation, and the only time that it actually gets turned on, the door gets opened up so that way that hot air can come in, is if the pilot commands it. And it's a good practice just to be, as you're flying around, if all of a sudden you need carb heat, that you put your hand on the carb heat knob and you pull it, and then like you leave it there, and so that way once you get your engine performance back, that icing has gone away, then the only way you get your hand back is if you push it back in, because what you don't want to do is start flying with the carb heat on all the time. Because if you get into critical phases of flight, like takeoff and landing, you're not operating with the full power of that engine, and it's something that's totally you can totally turn it off and get the power right back almost immediately. So it's just a good practice for anybody who's flying out there. But that's how carb heat works. Pretty straightforward. It's really just hot air being piped into it, but it's the primary way that we mitigate carb ice.
Lastly, and this should go without saying, is that you can't just suck up any old air into the engine. It has to be filtered, and it has to be filtered properly. If you have a situation where the induction system brings in really dirty air, well, that dirty air is going right into your engine. And we have systems in place to try to get all the dirt out of the engine so that way it doesn't mess up any operations. So let's talk about like air system filtering and what should we be cognizant of.
Okay, first let's just start talking about just the different types of filters that you can come across. The most common one is just going to be a simple paper filter. That you'll notice that these are all look wildly different than each other. They're all different sizes and different shapes because they all go into different types of aircraft, and they service different types of engines. So you have to make sure that you have the right filter for the right job, or else you're going to end up having a gap, or it won't fit, or something that will cause the filter to be basically ineffective at filtering the air that it comes across. Now, with that being said, what you're going to be looking for is making sure that, well, for one, you're going to change out the filter every annual unless otherwise stated in the maintenance manual. But you're also looking for making sure that the filter is not torn or somehow allowing air to get through it without being filtered, because at that point the filter becomes basically just pointless. You're also going to be looking to see if it's got a lot of trash in it. If it's a filter that you don't have to replace every single time, you're trying to save the customer some money. Is it completely like clogged up with grass clippings of doing a lot of off-airport kind of landings and that sort of things? But generally speaking, paper filters aren't that expensive, and it's best to just simply take them off and throw them away and put another filter in there. All right, so the other type of filter that you could potentially come across are these foam filters. Now, these foam filters could potentially have either oil impregnated in them, so that way they're kind of oily whenever you touch them, or you will like the Canyon filter that I was talking about earlier. You actually put oil onto, and what happens is that oil collects the dust. Now, they're extremely effective at getting dirt and dust and grime out of the air that's going into the filter. However, they're also really good at getting clogged up. So if you land in a really dirty environment, say off airport, dirt runways, that kind of thing, then you run a real chance of getting that thing clogged up. And so it's something you want to be cognizant of. Also, you could have these in a dry form as a pre-filter over a paper filter. So that's the way that the Cherokee is set up. Is so that way it has a pre-filter that goes over the top of it that catches all the big stuff and then lets the fine stuff enter in the filter itself to be filtered out of. So you could have either one of those options. Like I said, these are common on Piper Cherokees, and the paper filters are probably the most common out of all of them. There's also the possibility that you could have a metal mesh filter that's on there. Usually these are actually not typically just metal mesh. You'll have metal mesh that with a paper filter on the inside. Now these will be more expensive, significantly so, and it'll also be changed out far less frequently. And you might even have the possibility to wash these out and prolong their life. For an extended period of time, depending on what the manufacturer will allow. But just know that these could come across, and don't throw them away or anything because they're usually reusable and they're usually expensive.